Okay, here is a helper video for page 359. We are given imaginary numbers and we're asked to rewrite them in modulus argument form, also known as polar form. So one thing that helps is, first of all, just to graph it. So I'm going to make a little graph, and this is the real axis, and this is the imaginary. So here's the real part, +2. So I'm going to go 2 to the right. And then the imaginary part is 3 down, 1, 2, 3. And then draw it in as a vector. So here's my vector. So this is directly related to vectors in that you can write this point, this imaginary point, in terms of magnitude, so how long the vector is, and direction, which is the angle from the positive x-axis. Okay, so in order to find the magnitude, well, I can draw in my little right triangle, and the magnitude is the length of the vector. So I know this side is 2, this side is 3, so I can use the Pythagorean theorem. And when we do, let's see, what letters are they using in here? This is also called the modulus. We're going to call it R. Okay, so to find R, we do the square root of 2 squared plus 3 squared. And so that simplifies to the square root of 4 plus 9, which gives us the square root of 13. So that is our modulus. When we were doing vectors, we called that the magnitude. So you can think of it as really the same thing. Okay, and then the direction is going to be this angle right here. So the angle that is made with the positive x direction. So to do that, I'm going to use the inverse tangent function. So tangent -1 of opposite over adjacent. So katoa, opposite over adjacent, 3 over 2. And notice, actually, I should have said that's -3. I'm going to make it a -3. And we're going to put that into our handy dandy calculator. So I'm going to do arctan, or tan -1 of -3 divided by 2. And notice I'm in radians. I believe in the directions I said I wanted you to use radians in your answer. And so that gets me -0.983 if I'm going to 3 significant figures. And I also had said in the directions that the angle should be written between -pi and +pi. So pi is 3.14, so this is definitely less than pi. So this would be called my argument. That's my argument, is that one right there. So then if we were to write the answer for this imaginary number, if we're going to write it in modulus argument form, we would write, okay, so 2 minus 3i, if we're changing the form, it would be, we write the modulus first, square root of 13, and then we write cis, which stands for cosine plus imaginary times sine, or sorry, minus. Gosh, now I'm forgetting. Cis stands for, plus imaginary times sine of the argument, which is -0.983. Okay, so there you have it. That is how you do problem 2. So I'll let you do B, C, and D. All right, problem 3. Let's set up for problem 3A. It gives you, first of all, it gives you little information so that you don't have to grab your unit circle. It tells you that if you're looking for the tangent of pi over 6, that it's equal to 1 over the square root of 3, etc. Gives you little information. Okay, then it says, hence, write the numbers in the form r cis theta. So we're given 4 plus 4i, and they want us to write this again. They want us to write it in polar form, or this form right here. And but it wants it to be in exact values. We want exact values. So no fair using the calculator for the tangent like we did on part 2. Instead, we're going to be using that unit circle information they give us in the book. Okay, so they give us that unit circle information, but that's something that you should be able to, you should know, or be able to figure out by looking at your unit circle. Anyway, okay, so this is going to be exactly like the previous problem. So I'm going to go ahead and set up my imaginary axis and my real axis. And I'm graphing 4, 1, 2, 3, 4, and up 4, 1, 2, 3, 4. Okay, so here's my real axis, here's my imaginary. So 4, positive 4, and positive 4. So it's right there. So I can draw in a vector because when I'm changing it to the form r cis theta, I'm looking for the modulus and the argument. Okay, so I'm going to go ahead, let me get my different color. So I'm going to be doing this right here again. And you might notice right away that I have a 45, 45, 90 degree triangle. This is an isosceles triangle. So I actually already know what this angle is. This is clearly a 45 degree angle. So this angle right here is going to be pi over 4. I just recognize that immediately. So I don't even really have to worry about finding the tangent. I can just tell what that angle is. Oops, and I just noticed you can't see what I've been doing. Okay, so now I really just, all I need to do is find the modulus. So this is 4 units. This is 4 units. And then if you do recognize that this is a 45, 45, 90 degree triangle, there's a shortcut here which says that this length is going to be 4 times the square root of 2. Okay, if that is not in your wheelhouse, if you don't, if you're not comfortable with your shortcut triangles, not a big deal because you could still do r is equal to the square root of 4 squared plus 4 squared. So r is equal to 16 plus 16. So r is equal to the square root of 32, which simplifies to, this is 2 times 16, right? 2 times 16, square root of 16 is 4, square root of 2 is left behind. Okay, so there it is. So if you're comfortable with your shortcut triangles from geometry, it makes it really fast. I was able to just look at that and I knew what the modulus was. I was also able to just look at it. I knew that was pi over 4 because it's an isosceles right triangle. All right, so now I'm going to write it in this form right here. So it would be, my r is 4 root 2, and then cosine plus imaginary sine times pi over 4. There it is. Okay, so for problem 3, you want to put all of your answers in exact form. I'm looking at my answers that I made, and yeah, no problem with that. Put them all in exact form. Okay, next problem, problem 4. What is that problem 4 asking for? Problem 4 wants you to go backwards. Okay, so for problem 4, tilt this so we can see the bottom of the paper. Problem 4, I want to do problems A and B. Okay, so problem A, it says R gives me the modulus, and it gives me the argument. So basically, it's telling me that my number is 3 cis 60. Okay, so now this is actually super easy to change it back to rectangular form if you just know what the cis stands for. If you know what the cis stands for, it's super easy. But let's pretend you didn't for a minute. Let's do it the hard way. I'll do it the hard way first, and then I'll do it the easy way. So the hard way is just to, again, remember that this is a vector, and it's a magnitude and a direction. So notice this is in degrees, not in radians. So think about where's 60 degrees. 60 degrees would be about here. And my radius is 3. So this is going to be 3. Sorry, I made it way longer than 3. So that's kind of annoying. Okay, so now I want to change it into rectangular coordinates. That means I need to find my x value here and my y value here. And I know the angle here is 60 degrees. So I can just use basic trigonometry. I can just use basic trig to figure this out. To get x, that's the adjacent side. So I would say the cosine of 60 degrees is equal to x over 3, adjacent over hypotenuse. And then I can multiply both sides by 3 to figure out what my x is. And to get y, well, y is opposite the 60 degrees, so that would be sine. So sine 60 degrees is equal to y over 3. And then I can solve for my x and my y. X is going to be the real part, of my imaginary number, the real part, and y is going to be the imaginary part. It's going to be the part with I. Okay, so now there is actually a shortcut. By knowing what cis stands for, okay, the shortcut here is it's 3 times cosine 60 plus I times sine 60. And this does the exact same thing as solving these problems does. Because notice to get x by itself, I'd multiply by 3. And notice here, I have 3 times cosine of 60. And then for the second one, it's 3 times sine of 60. If I distribute this, 3 times sine of 60. And as I was saying, y is the imaginary part, so it's going to get an I with it. And x is the real part, so it gets no I with it. So here is the shortcut. Okay, and did they want us to do it in exact form? Yeah, they wanted an exact form, I believe. So cosine 60, that is, did I write it down somewhere already? No, where is it? Okay, so if I make my little unit circle, 60 degrees is right here. So if we're thinking about our unit circle, what are the coordinates right here? Well, this would be 1/2, and this would be square root of 3 over 2. The coordinates here on my unit circle are 1/2 square root of 3 over 2. So it's cosine sine. So the cosine of 60 is 1/2. So I'm going to have 3 times 1/2 plus I times the sine of 60 is the y value on the unit circle, square root of 3 over 2. And then I'm going to distribute my 3. And so I'm going to get 3/2 plus I times 3 root 3 over 2. And there it is. Okay, so you're going to do the same thing. That was problem A. Same thing for problem B. Okay, so you can do it the long way using trig, or knowing that this stands for cosine plus I sine, you can do it the fast way. Just figure out what's cosine of 60 and what's sine of 60. Here it is using the unit circle, but you could also, of course, do it with your graphing calculator, but then it would give you a decimal equivalent. So when it is something like 30 degrees, 45 degrees, 60 degrees, 90 degrees, all those nice unit circle degrees, chances are you should just use your unit circle. Okay, so that's it for a little helper video for page 359. Hope it helped. Bye-bye.